article from World Crunch just a couple of days ago saying artificial intelligence will kill capitalism. All right, that's a bold statement. That's, pretty much any headline these days, to get anybody to read your article, you need to make a very bold statement, but there's actually a little bit of a reason behind this. If you read it more carefully, essentially what they are arguing, and it's some food for thought as we work on artificial intelligence, is that once we can build an AI that is smarter than essentially all people, then the whole system we have in place right now, where you get paid based on how much you contribute to society, will not be that valid anymore, because now no people will be able to contribute all that much anymore. These AIs will do everything that needs to be done, and so we'll need a whole new economic system to kind of support how we live once AIs can do more than we can do. People talking about this are actually people you might have heard about. Ray Kurzweil, who's running a group at Google, and also in this case it's Sergey Brin pitching in. Essentially they're thinking 2045. Of course, who knows whether they're right, but I think in the very long term at least it's something to keep in mind. Google's actually been putting some thought into AI and the importance of AI for their business. So just about a year ago, they made an acquisition that was actually pretty substantial. So for over $500 million, they acquired an AI company called DeepMind, based in London. Now you might say $500 million, that's nothing these days. Every acquisition is $1 billion. But the thing that's interesting here is that unlike many of these billion-dollar acquisitions, which are usually based on how many users you have, how many people are using your app, whatever your latest fad is that you managed to make popular and people now want to monetize, this is actually based on buying a company that had no users. This was just about 30 people working on artificial intelligence, and Google thought these guys or girls, I don't know what the exact composition is, were making a lot of progress and that they would create a lot of value, and they decided to just put down roughly $500 million just for the people. All right, so informed search is a topic for today. How we'll break it down, we'll first look at a quick recap of uniform cost search, which is a type of uninformed search, which we covered last lecture. Then we'll look at heuristics, which is going to be the thing that informs our search. Then we'll look at a first take at using those heuristics called greedy search. We'll see that that's not exactly the way we want to use the heuristics. We'll get to something better called Hstar search. And then at the end, we'll look at something called graph search, which is a tweak to what we've been doing that will change all our search algorithms. It will change our depth first, breadth first, uniform cost, greedy, and Hstar. We'll have two versions of all of these, one that's called tree search, one that's called graph search. Okay, so search, what was it all about? We would formalize a problem that we like to solve as a search problem by defining a state space. A state corresponds to a possible configuration of the world or the part of the world that's relevant to the problem you're solving. There are actions that you can take from each state, and there are potentially costs associated with those actions. The successor function tells you, for a given state in action, which next state you land into. It also tells you for a given state what actions are available, so it describes the dynamics of the world. There's a start state, and then there's a goal test. And just a reminder, it's a goal test, not just a goal state in many cases, because there could be many states that achieve your goal. A search tree was a construct that we built as we solve a search problem. The nodes in the search tree correspond to possible plans. These plans could have costs associated with them. But part of the game, remember, was to not try to build the entire search tree, but just explore the part of it that's relevant to find a solution. A search algorithm is an algorithm that systematically builds this search tree, but hopefully not entirely. It chooses an ordering of expansion from the fringe. So the fringe is this data structure that keeps track of partial plans that you haven't further explored yet, and from which you choose one to further explore in every round of your algorithm. An optimal plan or an optimal algorithm is one that finds a least cost path that achieves the goal. All problems we've seen so far have been of the type, let's find a path, maybe to a goal, to eat some food pellets. Search is not just about finding paths. And towards the end of this course, we'll see many examples that are not pathing at all. They might relate to language, for example, translation or speech recognition. But before we get into those more kind of advanced applications, let's look at another example that is actually not pathing, but still a search problem. Let's say you have a stack of pancakes. And let's say this is your current configuration. You have a spatula. You can kind of go between two of them. And then you can flip the ones that are on your spatula. And this could result in this next state. You could go between somewhere else, get another next state. And you could go yet somewhere else and get another next state. So these are some possible next states based on the actions you can take. The cost here could be the number of pancakes you flip when taking an action. So if you go all the way to the bottom, you flip all 4 of them, that's a cost of 4. You go only halfway, you flip 2 of them, that's a cost of 2. All right, so the goal here would be to end up with the pancakes sorted with the biggest one at the bottom, smallest one at the top, and always going from large at the bottom to small at the top. So you might say, well, who might care about flipping pancake problems? Well, it turns out some people, most of you, not all of you know, actually have cared about this problem a lot. In fact, 2 people you probably didn't think would be hanging out together a whole lot. 2 people are Bill Gates and our Christos Papadimitriou. And they studied in detail this problem. It's a paper you can go read about. It's a while ago, but at that time they were hanging out. So what does the Statespace Graph look like? So this is what the graph looks like. This is looking at all possible states and how they can be, how you can traverse from one state to another state, as well as annotated with costs for each edge. How do we solve this with what we've seen so far? We could run tree search. So tree search, remember, this is the algorithm. You essentially have a main loop. Before you enter the main loop, you put the start state onto your fringe, which is shown here so far. So just one state on the fringe. And then you work through this loop. You check if there is anything left on your fringe. If there is, you pick something. Well, there's nothing, then you have failure because you didn't find a solution. If there is something left, you pick something. Your strategy will determine what you pick. In this case, there's only one thing you can pick, so you pick that. You then call your successor function, which tells you what the next states are. Well, actually, first you check if it achieves the goal. If it doesn't, then you call your successor function. Put the successors on the fringe. And then there are costs associated with this, and you repeat this process. Now your fringe consists of these 3 over here. You will again choose one from the fringe based on your strategy. Check if it achieves the goal. If it doesn't, you expand it and repeat. Okay, so that's what tree search is like and what it would look like on this pancake flipping problem. Okay, so here there's a path to the goal with a cost of 7, but this is just a small example. Now, the one thing I want you to keep in mind is that this fringe, this thing that keeps track of partial plans that might get expanded into your plan that you ultimately return, can be kept track of on a queue. In fact, a priority queue. And the only difference between these search algorithms we'll be covering would then be what type of priority system you associate with your plans. You could have priorities based on how deep you are in your search tree, based on how shallow you are in your search tree, based on how much cost you've incurred so far. And later we'll see how you can use heuristics to influence the priorities. Now it is true that if all you care about is depth-first search or breadth-first search, there are more optimized data structures you can use rather than just a general priority queue. But in this class, we're looking at it from the point of view of using a general priority queue as we're building up to Hstar search, which is ultimately the algorithm that we're striving for most of the problem we care about in this class. Okay, so uninformed search, which we covered last time, this case uniform cost search, kind of expands its way down this search tree according to how much cost has been incurred so far. We know it's complete and optimal. The bad part is it explores options in every direction and uses no information about the goal. So let's take a look at an example here. So what you're seeing here is an empty grid. You see a start state in green, goal state in red. As this demo runs, underneath it's running a search algorithm. The first time any given state gets its successor function called, you'll see a white dot appear for that state. So the order in which the white dots appear indicates when for the first time that state was kind of called inside a successor function. Now let's take a look at what uniform cost search looks like, executed on this particular grid. There's my cursor. Here we are. So it expands out equally in all directions. Now let's take a look at what this looks like in a Pac-Man maze. So this is a different visualization. This runs so fast it's already run, actually, the search. But what you're looking at here is a maze. There's one dot. The goal is to eat that last dot. So there's effectively one goal state here because there's one way to achieve that goal most quickly is by you end up in that dot. The red coloring of each of the locations indicates when that state was expanded for the first time during the search algorithm. The brighter the red, the earlier on when running the algorithm that state was expanded. So you can see right around Pac-Man, it's very bright red. Those states were expanded early on. The darker red, the longer it took for that state to be explored during running the algorithm. And if it's not red at all, there's actually one square that's not red near the top right that's still black. That state was never explored during the search. Now the bad news here is that all but one state was explored during uniform cost search to find a solution. We'd hope that we might be able to find a solution that with an algorithm that doesn't require visiting all states and exploring what would happen there. But this is what happens for uniform cost search in this particular situation over here. Now, what path did it find? This is the path it found. So the path it finds is not necessarily in the order in which expanded states. It expanded states in some order based on how close you are to Pac-Man, but then the path actually went through a pretty dark red part to get there. All right. So that's what we want to fix today, is to avoid exploring uniformly in all directions and somehow use goal information as we explore. So we'll call this informed search. The concept we'll use to inform the search is heuristics. One important thing to keep in mind is that the word heuristic is very often used in kind of daily life. Oh, I'm using this heuristic to get this done or something like that. When we say heuristic in 188, we mean something very concrete and very specific. It's actually a function. A heuristic is a function that maps from your state space to numbers and associates a real number with every state in your state space. You design it for particular search problems, and you want that number to reflect something about how good that state is. That's the idea. If you have a kind of heuristic that will help you a lot, it's one that tells you a lot about how good a state is in a very accurate way. If a heuristic that won't help you a lot, it's one that's not telling you much about how good a state is. Okay, so you can think of it that we now hook up some kind of measurement system to our search problems that can tell us how good any state is. Some might be good, some might be bad, so forth. So what would be an example heuristic? This is a Pac-Man search problem. Any ideas of what we might pick as a heuristic here? Suggestion here.
You might prefer spaces that are closer to the dot.
So you might prefer spaces closer to the dot. So one suggestion could be You measure the distance from each state to the dot, and that number is your heuristic. Of course, you can measure this in many ways. You could measure this with Manhattan distance. You could measure this with Euclidean distance. Since we can only walk horizontally and vertically, Manhattan distance probably makes more sense here. But in principle, you could also have a heuristic that measures it diagonally. Probably not as informative for this problem, but it would still be a heuristic, just not as good a heuristic as the Manhattan heuristic. What I mean with good for now is pretty hand-wavy, but later we'll get to a very formal definition of how good a heuristic is. So here's our pathing problem in Romania, and here is a set of heuristic values for each state. That's our heuristic function, right there at that table. In this case, it would be what's listed there is the straight line distance from each city to Romania, which is to Bucharest, which is the goal state. Why straight line distance? Because it's something very easy to compute. You just need to know the coordinates of the city. You don't need to solve a search problem to find out what the distance is from a city to Bucharest if you can just measure straight line distance. And often we'll want our heuristics to be pretty quick to compute because we'll use them inside a search algorithm to evaluate states. How about this pancake flipping problem? What could be a heuristic here? Any thoughts? Remember, we wanted to get them stacked. Biggest one at the bottom, smallest one at the top, and the cost of an action is how many pancakes we're flipping. Over there.
Correctly paired, like the smallest and the second smallest.
So you would look at every pair of pancakes next to each other and see if they are smaller onto bigger than, well, bigger onto smaller. So that'd be a measure of, that's a number you can compute for each state, so it's a heuristic function, and it's one that would be indicative of how good you're doing in that state. It'd be 0 if things were perfect, and it'd be a higher number if things were imperfect. The example we put on the slide, which is an alternative, is measuring the largest pancake that's still out of place. Because you know the largest one that's still out of place has to somehow make its way to the bottom still. The largest one that's still out of place has to make itself to its position. And so all positions from there up still will have to be moved around somehow for that one to fall into place. And so it tells you something about how many pancakes still have to be moved before you can achieve the goal. Okay. So this would be the numbers for this particular choice, but the proposed heuristic is just as well a heuristic as the one I put on the slide here. The simplest way of using heuristics is with an algorithm called greedy search. So let's look again at our pathing problem, but again, keep in mind, it's not just about pathing. There are much more complicated problems you can solve with search, but pathing is just a nice way to illustrate things. And let's run greedy search on our pathing problem. So the heuristic function is this table, and let's run greedy tree search. So tree search starts with putting the start state on the fringe. There it is, Arad. Then we check, is the fringe empty? No, so we can continue. What's on the fringe? Only one partial plan, only one node. Let's pull it off. Let's expand it. Let's check if it achieves the goal. It doesn't. Let's expand it. There are the successor states. Now we have 3 on the fringe. Let's look at the heuristic function. Well, first, let's see if the fringe still has anything left. Yes. Let's look at the heuristic function of the ones that are on the fringe. This one here is the lowest. This one here is the lowest, so let's pull that one from the fringe. Let's check if it achieves the goal. It doesn't. Then let's call the successor function on that one and expand. We'll go around. Now, this here is our fringe. We are back at the top of the tree search algorithm. Is there still anything on the fringe? Yes. So we continue. Among the ones on the fringe, let's pull one out. Greedy search pulls out the one with the lowest heuristic value, which in this case is the one over here with 176. We check, does that one reach the goal? No. So we call the successor function, include its successors, and continue. this point, we again are at the top of the algorithm. Is there anything left on the fringe? Yes. Among the ones left on the fringe, we pick the one with the lowest heuristic value, which is this one here, heuristic value of 0. We check, does it reach the goal? Answer is yes. We declare success. And this here is the path we return. Is that the shortest path to Bucharest from Iran? Not necessarily. It is a path, but we don't have any guarantees here that we necessarily find the shortest one. So that's one thing that can go wrong, is that you find a non-shortest path. In this case, you're digging for gold, but you end up with a much less desirable goal state, which is finding a shoe in your big gold mine. So what does it look like pictorially? So this is our search tree. We're steadily expanding that search tree as our algorithm runs. The strategy, namely the greedy strategy, determines in which order we traverse that search tree. What happens is that the best first thing, if you're lucky, takes you directly down somewhere. Because as you move along, probably the heuristic value will get lower and lower and lower. Now it's possible that the direction you're moving in is a dead end, and it seems like you're getting closer and closer and closer. And then you're going really, really deep in your search tree, you hit a dead end, and you have to look at other nodes in your fringe later and start again from there. If you're lucky, of course, the heuristic is so good that as you follow the one with the lowest heuristic, you keep getting closer and closer to a goal state that you can reach, and you'd solve the problem very quickly. So worst case, this is like a very badly guided depth first search. Best case, it's like a very well guided depth first search. But it's really depth first search kind of behavior, but based on the heuristic rather than based on depth. Okay, so let's take a look at what this looks like in our empty grid. So this is our empty grid again. Green is the start state, red the goal state. As before, states that get expanded get a white dot at the time of expansion, and so it signals to you the order of expansion. Let's run greedy search. Boom, straight to the goal. Because our heuristic value that measures distance to the goal tells us that that direction we're getting closer and closer and closer, and it keeps going that way. Okay, that's a great scenario. Now let's look at a more complicated scenario. This is Pac-9 in the maze again. The other example we looked at earlier. Again, the brighter the red, the earlier it was expanded in the search, the darker the later, and if it's still fully black, it was never expanded. So see, compared to uniform cost search, we're able to expand far less nodes this way, so that's a good thing. Computationally more expensive. Now, we also know that the optimal path actually went this way, and nothing here was expanded, so we know greedy search did not find that path. There's no way you can find a path if you don't explore it. In fact, the path it found, if we look at it here in action, it's this one here. Suboptimal, but found much more quickly. So there's a trade-off there. You might argue, well, if my problem is really big, uniform cost search might take too long. I don't want to wait for it. I'd rather have a greedy search return a solution to me than a uniform cost search I'm just waiting for, and it's too late by the time it returns a solution. Now, of course, ideally we'd get the best of both worlds, which we'll get through Hstar search. Let's look at a little analogy here that might kind of ring this home. So, anybody has heard of the race between the tortoise and the hare? See some nods. In fact, there's a Mercedes commercial on ESPN running these days that discusses this race extensively. Now, let's relate this to our class. The tortoise is slow and steady. That's uniform cost search. Kind of think everything through carefully, and then make your way. Hare just guns places and hopefully gets there, but might not get there. That's greedy. What we want to do in the rest of this lecture is find a way to achieve this. All right, so how do we achieve this with code? So combining UCS and Greedy, let's look at a very small example. We have a Statespace Graph on the left, a search tree, the full search tree on the right, just to illustrate what's going on here. Keep in mind, in a real-world scenario, you'd never build up that search tree, and you never built that Statespace Graph either. It's all implicit. But here, to illustrate some concepts, we're showing them on the slide. So what would uniform cost search do? Let's take a quick look at what's going on here. There's a start state over here, one goal state only over here. As uniform cost search starts its search, initially it'll expand this path over here, which corresponds to this exploration in the search tree. It won't stop there, but that's what it initially will do. Why? Because this cost is 1, this cost is 1, and this cost is 1. So it keeps things very cheap. And uniform cost search will try to exhaust all the cheap options before considering anything else. Okay. Greedy search will order by the heuristic. So greedy search will essentially look at H, which is giving it this sequence over here, the red sequence. Is that the optimal path to the goal? No, but it would just essentially, in a depth-first fashion, according to the heuristic, go down, let's see, this path over here, which is this one over here. That's the order in which it would explore the search tree, and it would return us that suboptimal solution, but would find it without having to traverse the entire search tree. How do we combine both? Well, there's a very simple way to combine both. It's to say, instead of looking at just the cost we've incurred so far or just the heuristic, let's sum them both together. So we're considering both at the same time. That's what Hstar search will do. That's how it chooses its expansion ordering. Now keep in mind, when I use this notation here, G is the backward cost. It's the cost you've encountered so far. For example, if you look at this node over here in the search tree, G is 4. It was a cost of 1 to go from S to A, and a cost of 3 to go from A to D. Sums up to 4. That's the backward cost. So the backward cost is something we accumulate over time, or as we traverse states. The heuristic is just a function associated with D. Right? It says for D, the heuristic is 2. It has nothing to do with how you arrived at D. It's just the fact that you have this table or a function in general that tells you for every state what the heuristic is. So there's 2 different calculations happening here. Heuristic is just a function call for a state. Backward cost is something you accumulate in this partial plan. All right, so when should Hstar terminate as we run this search? Let's say we run our Hstar search on this example over here. Right, what would happen? We have S, only one on the fringe, so we expand S. We have S to A, S to B. We need to look at the F cost, which is, so we have for A, G, SAG equals 2, H equals 2. Then over here we have G equals 2 and H equals 1. So we'll continue over here, expand B. We get G. For G, the G cost is 2 plus 3, which is 5. The H cost is 0, so we end up with a total of 5. Now if we run our algorithm naively, not the way we've defined it, you would say, oh, well, we have G on the fringe now. Let's just call it done. And you would find the path SBG. Now, we know that's not how our algorithm is defined. We have to wait till we actually pick something from the fringe before we can declare success. So we wait. We don't declare success yet. We look at our fringe. We say SA has a F cost of 4. SBG has an F cost of 5. So we need to go with SA and expand over here. This will have G appear again over here. The G cost here is 2 plus 2, which is 4. The H cost is 0. We still don't declare success. We go back around in our algorithm. We look at our fringe. We look at which node has the lowest F cost. It's this one over here. We check, does it reach the goal? It does. And so this is our solution we return. So it's really important to wait to declare success until a node that reaches the goal is pulled from the fringe in your algorithm. It's too early to declare success when you push it to the fringe. Okay, is it optimal? We know uniform cost search was optimal, but now we're adding this heuristic in the order in which we expand nodes. Is it still optimal? Okay, let's take a look here. If we run Hstar search on the correct we've already seen that if you run your search incorrectly, you declare success prematurely, it can be suboptimal. But now let's consider what happens if you do run your search correctly. Is it now guaranteed to be optimal? So we have S to A to G, an F cost of 1 plus 6 here, an F cost of 5 plus 0 here. We'll go around in our algorithm. We haven't declared success yet. We go around, look at our fringe, lowest F value here. We declare success S to G. What just happened here? That's not the optimal solution. The optimal solution actually goes through A. But our algorithm declared success for a different path. And we ran it correctly. Any thoughts? Yes?
The heuristic was not very accurate.
Exactly. The heuristic was a heuristic, but not a good heuristic. So when we run Hstar search, our heuristic has to satisfy certain properties, we'll see, to still obtain optimality guarantees. And this heuristic is not satisfying those properties. In particular, in this case, what happened is this heuristic here of 6 was so far off from 3, which was the actual cost from there, and it was not just off, it was a lot larger, meaning that this partial plan here from S to A did not get much priority, even though it should have gotten good priority, because it's actually a pretty good partial plan. And so by having this very high heuristic where it should be lower, the priority of this node is too low, and it doesn't get expanded in time. We declare success with the wrong path. Okay, so we don't want heuristics that are too high. That's the intuition here. We need them to always be less than the actual costs to guarantee optimality. That's what we call an admissible heuristic. Okay? So inadmissible or pessimistic heuristics break the optimality by trapping good plans that are sitting on your fringe and not letting them get out of the fringe, because they don't look good because of that pessimistic, inadmissible heuristic. Admissible, optimistic heuristics slow down the bad plans, because they know that this is a bad plan, you have a not so great value there, but don't slow down things too much to keep such that nothing gets stuck for too long on the fringe compared to how good they actually are. Okay, so let's make this formal. We'll define something new here, Hstar. Hstar is a function that's a lot like a heuristic function. In fact, it is a heuristic function, a very specific one. It's the one that for every state tells you the cost of the cheapest way of achieving the goal from that state. All right? So Hstar, cheapest way to reach the goal from state, or N here is a node, which is a plan, and then what that means is the cheapest cost with which you can complete that plan into a plan that achieves the goal. So sometimes we'll apply H to a state, sometimes we'll apply it to a node. When it's applied to a node, it's the same as applying it to the last state in that node. There's a bit of terminology here, but a node is a plan and a state is an actual state. Okay, so an admissible heuristic, Hn should lie between 0 and this Hstar special heuristic, which probably you never have access to because it requires you to know the cheapest path to the goal from each state, which is pretty difficult to know. But this is a definition we can nevertheless use. So let's look at some examples. We talked about the Manhattan distance to that one remaining food pellet. Is that an admissible heuristic? Yes. Why is that an admissible heuristic? You can only move horizontally and vertically. So really the best thing you can do is to move there in 15 steps, and that's assuming there are no walls. With walls, it's only going to take longer. But what you see here is part of what heuristic design often entails, is that you think of an easy thing to compute, that is the distance without walls, use that as your heuristic, and because with walls it's only going to be worse, it's actually going to be an admissible heuristic. Pancake flipping, remember what we had there was, at least the heuristic on the slide was the largest pancake still not in place. Is that admissible? Yes, that's admissible because the largest one out of place signals that that one still needs to be put in place. That means everything above it still needs to be flipped somehow because that's how you move things around. So the minimum cost is at least the largest one still out of place. Okay? Coming up with these admissible heuristics is in practice most of what's involved in using Hstar. Why is that? We'll see a little more about Hstar in this lecture, but once we've covered this, you've seen most of what it really is, Hstar. It'll be an algorithm, it's something you implement, and once it's implemented, it's applicable to any search problem that you might encounter. But whenever you encounter a new search problem, how efficiently Hstar will solve your problem will depend on the quality of your heuristic. And those heuristics, you'll have to come up with in a very clever way for each problem that you encounter. So, let's take a look at how we can argue that indeed Hstar tree search is optimal. Okay? We'll assume admissible heuristics here. We'll already know that if a heuristic is not admissible, we can find counterexamples showing it's not optimal. Question there.
Question about the pancake flipping. It seems like you could solve that previous example in 2 moves.
Correct. So you could solve this in 2 moves. And so a lot of how you define the heuristic will relate to how you define the cost of your actions. And so we define the action cost not by every action being cost of 1, but the cost depends on how many pancakes you're moving around in a single flip. But that's a great observation, absolutely. So, let's look at how we can prove optimality of Hstar tree search. Let's do this in some sense by counterfactual reasoning. We'll have A be the designated optimal goal node. We wish that our search algorithm would arrive at A in this search tree, expand it, and be ready to expand it right before it expands it, realize it reaches the goal, and declare success. B is a suboptimal goal node. Any suboptimal goal node in the search tree. H is admissible, we'll assume that. We'll prove optimality by showing that A will exit the fringe before B. And since B is generically any suboptimal goal node in the search tree, well, if the optimal goal node exits our fringe before any suboptimal one, that means the algorithm always finds the optimal one. So let's see if we can prove this. So we want to prove that A, the optimal way to reach the goal, exits the fringe before B, which is a suboptimal way of reaching the goal. So imagine B is on the fringe. If B was never on the fringe, certainly B would never be expanded, and so we would have no issues, we'd already be done. But let's assume B is actually making it onto the fringe. Okay, so maybe the fringe, the expansion looks something like this. The fringe being kind of the bottom kind of curl on that expansion. Then some ancestor n of A is on the fringe too. Could be A itself, but something, either A or above A, on the path to A has to be on the fringe. Because the only way all ancestors of A and A could have disappeared from the fringe is if we had already expanded A, which means we already found A and we're already done. So some ancestor of A has to be on the fringe, could be A itself. Okay. Now our claim will be that this ancestor will be expanded before B. If we can prove that, then we can iterate this argument and say, oh, this was the current ancestor of A is expanded before B. After that's done, there will again be an ancestor of A on the fringe. That one will also be expanded before B. And this will keep repeating until we expand A before B, and we show that, indeed, A star finds A and not the suboptimal goal B. Okay, so let's take a look at this. Can we prove that N will be expanded before B? The F cost for N is less or equal than the F cost for A. Why is that true? Well, let's expand on that. So F of N is the backward cost to achieve N plus the heuristic H of N. That's just a definition of F cost. The F cost for N is smaller than or equal to the backward cost for A. Why? Well, A is supposed to be reach the goal in an optimal way, right? And we're on this path there that's not there just yet, but almost getting us there. We're at N. And the heuristic value, H, is admissible, which means that F of N is going to be smaller than G of A. That's the definition of admissibility. Your F cost, which is your G cost plus your H cost, is such that, by definition of admissibility of H, it's smaller than the actual cost to reach the goal. G of A is equal to F of A because at the goal, the heuristic is always 0. Otherwise, you have an inadmissible heuristic because the heuristic needs to be an underestimate of how much it takes to get to the goal. If you're at the goal, the only underestimate that's bigger than or equal to 0 is 0. So if we chain this together, we get that F of N is smaller than or equal to F of A. Okay. Then next we're going to show that F of A is less than F of B. How do we know that? Well, G of A is less than G of B because we just assumed A is the optimal way of reaching the goal, B is suboptimal. The way you measure optimality is by G. How much cost did it take to get there, to goal through A or to goal through B? So G of A is smaller than G of B. Now, the heuristic is 0 at the goal states, so then G is equal to F at the goal state, so F of A is smaller than F of B. Okay. Now, chaining those together, we get F of N is less than F of B, which means N is expanded before B. Okay. We repeat this argument, right? And we get that all ancestors of A get expanded before B. That means A will expand before B, and A star tree search is optimal, assuming an admissible heuristic. All right, I encourage you to work through that proof again in your own free time to make sure you can reconstruct this yourself, because there are things we might do, like test you on, let's say, give you a variation of an algorithm, see if you understand whether that algorithm is still optimal or not as guarantees. So it's important to not just know that A star is optimal, but also understand why it's optimal so you can do similar reasonings about similar algorithms in the future. All right, let's take a short break here, and after the break, let's study some more properties of A star. One thing that came up during the break, and I want to highlight here, in fact, one of the GSIs brought this up as an interesting point to highlight on this slide, is when you look at A and B here, there are different ways, there are different points in the search tree. Both A and B are plans. Both A and B are plans that achieve satisfaction of the goal test. It's possible that they achieve the satisfaction of the goal test by reaching different goal states. It's also possible they reach satisfaction of the goal test by reaching the same goal state, but by traversing a different path in the graph, but ending up in the same goal state. So both of these are possible here in terms of how you could have different nodes in your search tree that both achieve satisfaction of the goal test. Could be the same goal state or it could be a different one, It'd still be different places in the search tree either way. Just something to keep in mind. Okay, let's look at a few more properties of Hstar. So we've looked at uniform cost search. We've kind of augmented in some sense, stapling on top the Hare to get the heuristic incorporated. Question here?
So if the heuristic is admissible, it guarantees optimality, right?
Correct.
But does it matter how good the heuristic is in terms of how fast we reach the optimum solution?
So the question was, when the heuristic is admissible, it guarantees optimality, and the answer is yes. The follow-up question was, does it matter once your heuristic is admissible, what you choose, or is being admissible enough? And that's going to be a lot of what we'll look at in the rest of this lecture. What makes for a good admissible heuristic versus not so good an admissible heuristic. So you're thinking along the right direction, but I'm going to have you have some patience till we get to it. So we can look again at contours, right, of what states get expanded during the search. And let's look at the empty maze demo again and see what happens for Hstar search. So just as a reminder, this was uniform cost search. Okay. This was greedy search. And this is Hstar search. Now the exact pattern you get for Hstar depends on the exact heuristic you're using. In this case, the heuristic used is essentially half of the Manhattan distance to the goal. You might say, why not the exact Manhattan distance to the goal? That might be better. Yes, that is better. But to illustrate the point that typically you don't have such a perfect heuristic available, this is more illustrative of what an expansion pattern for Hstar could look like for a reasonable heuristic, but not the perfect Hstar heuristic. Okay? Then let's take a look at Pac-Man in the maze and see what the expansion pattern looks like there. So this is the Hstar expansion pattern. We see this is using the Manhattan heuristic. We see it hasn't expanded as many states as uniform cost search did, because uniform cost expanded all but one. It expanded more than greedy, but it was able to use that to its advantage to actually find a better path. If you execute the path found by Hstar search, it's this path over here, which is the optimal path. Now, if you look at this again, you look at the color coding. Again, brighter means expanded earlier on, and darker means expanded later. We see that initially it's expanding in this direction because the Manhattan heuristic thinks that these are really good states because it doesn't account for the walls. So first it's spending some time here. After a while it realizes that this is actually not as good because it has to move on its way back here where the Manhattan heuristic is increasing again, the path cost is increasing, and then it starts exploring out here. It also explores a bit out here because maybe this could actually be a good solution if there were no walls there. Remember, the way it expands, it doesn't know about walls in terms of prioritizing things, right? And so finally then it expands this way and it finds a path to the goal. And once it pulls that goal, the node that achieves the goal from the fringe, assuming it was an admissible heuristic, it knows it's the optimal path and can declare success. So Hstar mainly expands towards the goal, but it hedges its bets a little bit. It's not just looking at the heuristic, it's also looking at how much cost have I incurred so far, because I don't want to go down a path the way greedy goes down past that. The future looks bright, but you might already have incurred a lot of cost from that state. Okay, so here are videos of the same demos for in case you want to rewatch the demos yourself. Here's the comparison. On the left, greedy, you see the states it expanded and in which order. Remember, it didn't find the optimal path, and uniform cost search did find the optimal path, but expanded a lot of states. And then there's Hstar, which expanded a medium amount of states and found the optimal path. All right, what are some applications of Hstar? Well, there are many actually. What you see there is StarCraft, which actually we'll have a half lecture dedicated to towards the end of this semester, when we know a lot more of everything that can go underneath building an AI for playing this game. So video games have a lot of routing. Hstar could come into play there. Resource planning problems. We have to think about, first I need to collect these resources so then I can build this, which in turn allows me to build this. Well, think of what I'm talking about there. That's like calling a succession of successor functions where you say, from here I can get there, from there I can get there, and so forth. That kind of sequence of successor function calls, that's planning. You can use Hstar to solve that kind of planning problem just as well. Robot motion planning. You want to find a short path for a robot, maybe from wherever it is now to grasp a pizza from your freezer and put it into the oven. Robot, let's see, language analysis. Parsing language into what are verbs, what are nouns, and so forth. Getting the entire syntactic parse tree out, that can be solved with Hstar. Machine translation, the most efficient algorithms there tend to use Hstar underneath. Speech recognition, same thing there. When you think of these later ones, you probably don't think of them as some kind of pathing problem, but later when we cover them in more detail, you'll see that we can formalize these as pathing problems. We'll also need to see more about machine learning before we can do this, but they can be solved with Hstar once you have set it up the right way. Okay, let's take a look at a few more demos here. For this one, you also have to look at the console to get the full picture, what's going on. So, the bottom will matter most. So what's going on here? This is a maze. Pac-Man's goal is to have all the dots eaten, which can be achieved in multiple ways. So there will be multiple nodes in the search tree that achieve the goal. In fact, there will be multiple nodes that achieve the same goal state, because it could be multiple paths that end up Pac-Man in the same final location with all the dots eaten. But then there are also other goal states where Pac-Man ends up being at a different location with all the dots eaten. What we're going to see in the console here is a little bit of information about how much computation is happening to succeed. So it's going to run uniform cost search. We're going to see how many nodes it expands in the search tree, and then it'll execute the path it found. So searching for a path, it expanded about 8,000 nodes, close to 9,000, found the optimal path, then executed it, and so it executed the minimal cost path to achieve the goal, but it took almost 9,000 nodes to be expanded running uniform cost search. Now let's see what happens when we run Hstar search. I'm not going to tell you what the heuristic is, because part of the fun of Project 1 is going to be for you to think about heuristics for this type of problem. But remember, almost 9,000 nodes expanded by uniform cost search. Let's see what we get now. Starting the search, boom, done. 177 nodes expanded. That's it. From almost 9,000 to 177 with what is a pretty good heuristic, which hopefully many of you will come up with in your Project 1. Okay. Then let's do something else here. We're going to just play a little game again. The game here is for you to guess which search algorithm is being run, just kind of as a check-in on whether you're on board with what the different search algorithms do, and also just for fun. So, what are we looking at here? Let's see. So this is a water maze. Dark water is deeper water, has a higher cost to traverse than shallow water, which is the lighter shade of blue. So the top region is cheaper than the bottom region. You can imagine that the optimal path will mostly or maybe entirely go through the shallow region, depending on the exact cost difference between the two. Just as before, what will happen is, as I choose a search algorithm, which I'll do by hitting a key on the console here, but you won't know which key I hit, you'll get to see why dots appear in the order in which states get expanded during the search. Your job, so to say, is to call out which algorithm is being run based on what you see happening on the screen. So let's start out. First one here. What's this one? Okay, I'm hearing a mix of things. Let's have somebody raise their hand. What do you think, maybe, without raising your hand? So the suggestion here was uniform cost search. Any other suggestions over there? Breadth first. Any other suggestions? So we have two options here. Uniform cost search and breadth first search are very, very similar. In fact, they are identical if the cost of every action is the same. But in this case, the cost of every action is not the same. Right? The cost of the action depends on whether you're in shallow or deep water. So to see whether it's uniform cost and well breadth first, we need to look at whether the expansion slows down in the deep waters or not. If it slows down in the deep waters, it's uniform cost search. If it goes at equal rate through deep and shallow water, it's breadth first. So let's take a look again. What happens? It's going at equal rate no matter where it is, so this is a breadth first search. All right. Now, let's take a look at what uniform cost search would look like. I'm giving it away, but just because we're talking about it here. So it would expand with this pattern, which is a little different from breadth first search. We'd also find, in this case, apparently this is the optimal path. All right, let's try another one. See what you think it is. How about this one? Hare greedy. Why? Because a state that's closer to the goal gets favored in expansion, and it keeps getting closer and closer, ignoring the fact it's incurring this large amount of deep water cost. Okay. How about this one? Depth first, right? Okay. Now, how about this one? So I'm hearing Hstar. Why is that Hstar? Well, it's mostly diversing the shallow waters because those are cheaper and the backward cost is small, but it's also accounting for the heuristic, and that way it really edges towards the goal and gets there with the shortest path. Yes?
For the depth first, why were there a couple of dots that were?
Say it again?
For the depth first search, why were there a couple of dots that were still white?
Okay, let's take a look at it again. Depth first search. So the question was, why were some dots still white? What happened here is that it did a search. The green dots are the path it returns. The white dots are the states it expanded along the search. And so apparently the path it found doesn't traverse those white dots. Not sure exactly why this happened here. We'd have to look in the details of its expansion ordering and so forth. But that's what it means. Question here.
I think it's because the very first path that goes all the way down to is a dead end, and then the next path that looks like doesn't go to those dots.
So that might be true that there is a dead end there in the search, maybe related to the fact that it's actually running a slightly, it's running a search where it's maybe not allowed to go back into the start state. It's maybe not allowed to enter that, which would make it a dead end there, and we might make it follow a slightly different path. We'd have to look at the specifics of how it exactly run, what the order of expansion was to know exactly what happened. Okay, So we know what they look like, these algorithms. Here are some videos to enjoy those algorithms in action again yourself. Now let's get to what we need to do in practice, which is build heuristics. Okay? What's an admissible heuristic? It's something that's cheaper than the true cost of the goal, right? Simple case was straight line distance for a pathing problem. Assuming the world is flat, I guess, or well approximated, I guess. Even if the world is not flat, it'd even be shorter because you're cutting through the crust of the Earth. Then Manhattan distance, ignoring walls. That's admissible because it's cheaper. The shortest path without walls is cheaper than the shortest path when you do consider walls. And so this is something that will often come up as you create heuristics that are admissible. One way to get there is to think of, how can I simplify the problem, make it easier? Take some constraints away. So a constraint in the routing problem was that you need to follow the roads. Let's take that constraint away. That way you have more options. You could still follow the path designated by the roads, but you have more options. For those more options, it happens to be easier to find the best solution, very quick, and you use that as your heuristic. Same for the Pac-Man problem. When you remove walls, you have more options. And sometimes it's a search problem again, to find the shortest path for this new search problem, where you have more options available in every state. But it's a very special search problem where it's very easy to know what the optimal solution is, and so you can just compute it right away without actually running a search algorithm. Okay. We'll later see sometimes inadmissible heuristics are useful, but let's not worry about that too much for now. So let's look at this 8-puzzle problem. 8-puzzle is this game that used to be popular, I guess, before other games came into existence. What you do here is you slide one of the tiles into the open square. So you could slide a 2 into the middle, the 5, the 6, or the 3. Then a new square will open up. You can slide something in there. And the goal is to end up with this nice configuration over here. So what are the states? It's all possible configurations of these pieces. How many states are there? Well, let's see. The first tile you could place in any of 9 locations, right? The next one you could place in any of 8 of the remaining locations. The next one, any of the remaining 7, and so forth. The last one, you'll have 2 locations left. So essentially, it's 9 factorial, because the multiplication with 1 is not going to change it. And so you have 9 factorial possible states. What are the actions? You can move something into the empty square. Another way to think about it, you can move the empty square in any direction, but not out of the board, of course. How many successors from this start state? 4, because there are 4 tiles that could be moved into that spot. What should the cost be? Well, that depends. You define your problem. You say what it costs you. If you are like most people, you might say the cost is 1 every time you take an action. And you want to find the solution that has the minimum number of moves. But maybe you really don't like to touch the square with the number 2 on it for some reason. You can give a cost of 20 for having to touch that square and move it. That's fine. That's your cost function. You can do whatever you want. That's the definition of the problem. Our algorithm will then solve the problem. Okay, so here's the first heuristic we could consider. The number of tiles that are misplaced. Why is this admissible? Well, every tile that's misplaced needs to be moved at least once. If our cost is indeed how many moves we need to make to get to the goal, this is admissible. What's the heuristic at the start state? Well, we'd have to count how many of them are out of place, right? This one's out of place. Well, let's start at the top. This one's out of place. This one's out of place. This one's out of place. This is the goal. This one's out of place. This one's out of place. This one's out of place. Oh, all of them are out of place. Look at that. So 8 of them out of place. Heuristic value would be 8. Now, if we run with this heuristic value, you can evaluate how many nodes are expanded. That's something you would do to evaluate the quality of your heuristic, right? And so uniform cost search, for a simple initial start state where you only need 4 steps to reach the goal in a goal state, or the goal state in this case in an optimal way, requires 112 expansions. The tiles heuristic reduces that to 13. If your start state is 8 steps away from the closest possible goal state. Uniform cost search will require 6,300 expansions, and Hstar, with the heuristic we're considering here, will require only 39. If your goal is closest goal is 12 steps away from your start state, you'll have about 3.6 million states expanded with uniform cost search. Hstar, just 227. So we have a big benefit here from using Hstar. It'll still find the optimal solution because it's an admissible heuristic, and it'll find it much more quickly. Okay, this is a relaxed problem heuristic. It's one way to think of it. We said it's an admissible heuristic because we can reason that every tile has to move at least once to get in place. Another way to reason this is to say, let's consider it a new problem where we expand the action space. Instead of just sliding, you can just also, as an additional action, grab any tile and put it into its spot. Larger action space, still a search problem in principle, but one that you can solve very quickly, because now the optimal solution is to just, one by one, put them in their correct spot, and you're done, and that's the heuristic we have. Okay, now, can anybody think of a better heuristic that's still admissible? Any thoughts? Over there.
You can take the.
I'm actually meant somebody else, but we'll get you next time. I'm sorry. I was trying to point over there. Okay, so this suggestion was a distance every tile has to be moved. Okay, let's have you go next.
I have the same thing.
Same one. Okay, so the suggestions in both cases, which reinforces it pretty well, is the distance each tile has to be moved to get to the goal. Okay, that happens to be the one on the slide. Not sure if people looked ahead or came up with it themselves, but let's assume they came up with it themselves. It's a pretty clever heuristic. It's good. So that we'll call it total Manhattan distance. Why is this admissible? Well, you can reason about this. You can say, well, everyone has to move at least that far, and we can only move one thing at a time, so at least that many moves will be required. Another way to get to this is to say, let's relax the problem and introduce more actions. We're going to, like in Pac-Man, where we got rid of the walls. Here you say, you can move anywhere with your tile, ignoring the presence of the other tiles. Now the action space is larger. It's not the original search problem anymore. It's a relaxed one. It's one that's very easy to solve because now you would just move every tile to its goal location. Of course, only one step at a time, and you get this heuristic as the optimal solution for this relaxed problem. So again, the optimal solution to the relaxed problem is giving us a heuristic that's admissible, and that's true so by definition because that's how we define a relaxed problem. A relaxed problem is one that gets rid of some of the constraints, opening up more solutions than we had before. But of course, for a relaxed problem to be useful, it also has to be very quick to compute the solution for that relaxed problem. Okay, we can compute that for the start state, adding it up for all tiles. Now, here, look at the previous one. We had 227 still. This brought it down to 73 expansions. Okay. What about using the actual cost? The actual cost to reach the goal. Hstar, as we denoted on an earlier slide. Would it be admissible? Yes, because it's smaller than or equal to Hstar. Would we save on nodes expanded? Oh, we would save a lot. It would be very informative, right? What's wrong with it? Well, with Hstar, we kind of have a trade-off between quality of estimate and work per node that we typically encounter. In this case, we would do so much work per node to get that value Hstar, we'd be running a search inside the search every time, right? We'd have to solve the problem to get our heuristic. And so that's not going to be efficient overall. You have very few nodes expanded, but your overall computational efficiency would be low, and so you need to keep track of that trade-off. So it's not just about being closer to Hstar, but in principle, closer is better. Let's formalize this. So something called a semi-lattice of heuristics. And you can look at all possible heuristics that you could consider for search problem. And we'll define dominance between heuristics as follows. If heuristic A is always larger than heuristic C, meaning for all states it's larger, then A dominates C. Based on that, we can put all the heuristics in a lattice where this Hstar is sitting over here, because that's the highest admissible. You can't go higher than Hstar because then you become inadmissible. And everything 0 is the trivial heuristic. You can't go lower than that because you have to be at least 0 to be admissible. And so you can order them. Heuristics are not always perfectly orderable. It might be that, in this case, in one state, HA is larger than HB. In another state, HB is larger than HA, and so they're not comparable. And you don't have a direct vertical connection between them, or vertical path. One little trick that's useful is that if you have two heuristics that are admissible, the max of those two heuristics is also admissible. Because all you need to be is less than the distance to the closest goal. If both of them are less, the max of them will also be less. So if you have two incomparable heuristics, you can get the best of both worlds by just taking the max, which will dominate both of them. Okay, let's stop here for today.